So we continue with this section. Frobenius map. This is section 5, the reciprocity map. We're going to do proof of the lemma we just saw with phi, sigma, the element of the semigroup, with phi has image map to 1, sigma map to n. If big sigma is the fixed field of the small sigma, and to cast element small a in a sigma, then we claim to have the following relation. Maximum ramified subextension denoted by sigma 0 is of degree n, and its scalar group is generated by the Frobenius automorphism. As we discussed, this is always true for the Frobenius into the restriction. Consequently, the norm sigma 0 k is phi n, as we showed, because phi n is of this form, and as this is a group of order n generated by so this is exactly the norm map. On the other hand, one has the composite of this sigma okay delta is L delta. And the intersection is sigma 0. This is the definition of sigma 0. Here it's because that we know why this subextension, maximum ramified subextension is of degree n. We know that sigma is the element of the semigroup frog, and as a result, before we know that it is actually the Frobenius element of the subgroup of the Galois group. This subgroup. Here we mean that sigma is inside the subgroup. Actually, it's not this one because sigma was taken from L tilde over K, so it is actually a subgroup of L tilde over K, so it's inside L tilde over sigma. But the theorem we saw before tell us that we take any element from the Frobenius group alter it over k, then you just have to look at its fixing field. Then sigma tilde is always L tilde, and this element becomes the Frobenius element of this group. So back to our situation here, we know that sigma is actually the Frobenius element of sigma tilde over sigma. Knowing that decay sigma has index n, so sigma restricted to k tilde mapped to n under decay. As we written here, we have this relation. Then we ask, and this will imply that the inertial degree of k over sigma equals n. We know that the inertial degree of L over k is the dimension of the field extension of the maximum ramified extension of k inside L. So it's L intersected with k tilde over k. So in our situation, we know that sigma is over k, and the inertial degree of sigma over k is n. It's better to write sigma over k. This tells that the dimension, exactly the dimension of sigma intersected with k tilde over k is degree n. And the sigma tilde is k tilde as by the result before. Therefore, we have the norm sigma over sigma 0 is the same as norm over a sigma. The equality here is obvious. The norm of sigma over k, the norm of sigma over sigma 0, and the norm of sigma 0 over k. That's the general property of the norm. And we know for this part, because of the Gala group is generated as a cyclic group by a generator form for this ramified extension, we have this equality. This part is A raising to phi n. Actually, it's this one. And for this part, why we call it norm over A sigma? This is the definition of this notation, and defined with the normal L theta over K theta. But L theta here is sigma theta. So the K theta, where it's intersecting sigma is sigma 0. And therefore A is taken from A sigma. Here is from A L tilde. But what's the relation between A fixed line G L tilde and A fixed line G sigma? The relation to this G L tilde is a subgroup of G sigma. So the fixing point of A by G L tilde contains the elements fixed by G sigma. So a given element of A sigma is actually containing A L tilde. This norm map is from L tilde to A K tilde, in particular for A sigma, and A sigma is the same norm. I have to show that the norm sigma over sigma 0 is the norm L tilde over K tilde restricted to A sigma. One has that sigma intersect with K tilde is sigma 0. The relation of elements of this color group L tilde over K tilde with the norm of sigma over sigma 0. It's not very clear. This is left as exercise. So with this result we continue subgroup, which is generated by all elements of the form. Where U is an element of U L tilde. Tau is an element of this color group. This whole subgroup is mapped to 1. So the norm factored through this quotient, which is by definition homology group at each 0. In this group we have the fully memory. If element of this group is fixed by some element sigma in the Galois group of L to the lower k, such that this is a Frobenius element, in other words, X is fixed by sigma is written in this form. Then we have the complement at the norm of X. It's inside the norm of L tilde over K acting over U L tilde. Let's see the proof. Suppose X is U, will give it a subgroup. And suppose phi x multiplied by the inverse x equal to 1. So that we have U to the power of phi minus 1 This is because the subgroup is generated by all elements of the form. U is inside the UL tilde, and the tau is some element of this Galois group GR tilde over K tilde. So U Frobenius minus 1 acting on it is equivalent to 1 modulo this. So this means that I fall into this subgroup, but this subgroup is generated by elements of the form Ui of dou I minus 1. That's it. So now let them over K be a finite Galois subextension of L tilde over K. In order to prove that norm of U is inside norm of L over KUM. You see, finally we want to prove is for L tilde, but L tilde it may not be finite Galois extension, so we first look at those finite Galois extension of this L tilde over K. In order to prove that the norm of U is inside the norm, so U is any element in this subgroup such that fixed by -1, which is what we want to say. In order to prove that this, we may assume that U, Ui are inside Um. L is containing M. Let M be the dimension of M over K. And sigma for this given Frobenius, sigma be the nth power of Frobenius. And let M contain the big sigma, the fixed field of small sigma. So phi still in this group is in the Galois group of L total over K. And as we know the fixing field of sigma, then this Galois group is sigma tilde over sigma is generated by this sigma element sigma. By restriction, of course, because the L tilde is sigma tilde and sigma is a bigger subfield, so this is smaller. So this is sigma actually fall into this subgroup. And its fixing field is here. And this N here should be F of L over sigma. Chi over sigma maybe. Sigma over sigma with the unramified extension of degree N. The fixed field of sigma N. If this is N, it's containing sigma, but because this has F, inertial degree N, this is not very clear at this moment. by result 5.1. We can find elements whose norm is this element u. And similarly for ui, because u is inside um, so if element of u sigma n going to the norm sigma n over sigma, you map u total to u sigma, right? Again, sigma n is the product sigma I from 0 and minus 1. So this is unramified, so this is reason to. So this one is okay, but why we have this? Well, it's from sigma into sigma, so all the elements fall into u sigma. But what we took, we assume the elements are in from um. Maybe we have to go back to 5.1 to look more. Unramified finite extension over K. You have to record this HI. These are the tactical homology. What we wrote there was for unramified extension. So the norm of L over K over AL acting over quotient from AK, and H minus 1 is those are norm, trivial norm, and you quotient by those the subgroup generated by the elements of the form acting for beneath that multiplied by inverse of this element. It is simply the group. If it's cyclic, if this group is cyclic, then it's simply the group just acting by this generator. Otherwise, you have to keep all the elements of this group acting to act on it and multiply by minus this element. But if you look at this equality, the norm of an infinite extension is the intersection of the finite extension norm. In this case, we know any element here is containing all the finite extension. In particular, we can find element for this particular finite extension sigma n over k. Okay. By star, the elements u tilde phi mono phi minus 1 and the product of ui tilde tau I minus 1 only differ by element. X tilde u sigma n such that the norm is 1. Here the problem is what we know is for u and ui, but here we're comparing u tilde and ui tilde. Without tilde, they're the same, so we have the tilde when we know that we're applying the norm, it is a given one. So they differ by some element have norm 1, hence again by 5.1 they differ by element of the form. Yeah, that's because each minus 1 is 1. So any elements have norm 1 is the image of some elements of the form acting by sigma minus 1. We may thus write u tilde phi minus 1 equals y tilde. Phi to the power n minus 1 product u. So ui tilde. So this element and this element. So I suppose they differ by this element. And because we know sigma equals phi to the power n. Sigma, of course, is some power of phi. Actually, no, because we define sigma. Okay, we define sigma. We'll first fix some m, and we define sigma to be this way. If one sigma is defined to be this way, then we may know that something happened. For the fixing field of sigma and m, there are some relation. Because if the inertial degree of the fixing field of sigma over k is n, then why not okay, so the inertial degree is 1 is n, sorry. But we cannot see too much thing. Okay, I don't understand why we need this n here. Maybe it is used later, but anyway we have this. Okay, applying the norm n gives norm of u phi minus 1 equals norm of this one phi minus 1, so that norm of u equals norm of this one multiplied by something z, such that when you apply in phi minus 1 it is 1. Therefore z satisfies this relation. This inside u p tilde. Finally we use this and we see that For me, it's always a little messy to look at the index. You see if the Frobenius as a generator of this group. And if it fixes Z, then Z of course is in the fixing. It's inside the things of K. Okay, it's in UK. Finally applying sigma n, we have this is what I told. Sigma n is the norm, it's inside the UC. We obtain observing norm n equals dimension m over k, and using 5.3, what we proved just now. Okay, what we have is norm of u equals norm of u total applying sigma n. This is from 5.3. This relation with normal u total and normal y n. Sigma fixed z, so this is Zn. Z is inside UK, so the image of Z is inside UN. Y is inside U sigma, so the norm is inside M over K over UN. U equals U total sigma. This is by definition of U total. And it's by this one directly we have this. Okay, by definition of y we have this. And the norm of sigma over k is inside the image of norm. This one equals this one. It's by 5.3. This should be inside UN. What is the relation of sigma and n?